Excellent. So welcome to sunny San Francisco. Uh, I don't know where are you, but the place where I am, it is completely dark, like in the middle of the night. I guess if you are somewhere in San Francisco, it is the same situation. So what to do today? First, you've seen that homework that we have. So it would be good idea to start working on homework so that you don't that you are not late with that. So we have enough time, but if you start on time, it is going to be better than if you go later. So that's what we suggest. Today, we have to study the last part of syntax. And this is the packet of slides that come with the textbook. And textbook is Weber textbook. It would be good if you want to completely remove your cameras. I have that cameras are here, so I see plenty of people on your cameras. Just turn off that, please. Today we are going to speak about relationship between syntax and semantics. And then the slides that I have here are slides from Weber's book. There are, let me put it this way, there are 40 slides that we want to study because they are related to your homework. So it is useful to go through this part of Weber's textbook. This is chapter 3 from Weber's textbook. And also you have this posted on iLearn. So you can either download all these slides from the textbook website, or you can take from iLearn this chapter that is called Where Syntax Meets Semantics. And Weber starts by showing 3 equivalent grammars, G1, G2, and G3. He wants to define an expression, simplified expression, to show how this works and how syntax and semantics are not independent. So what he has is the first grammar that says sub-expression can be A or B or C or sub-expression minus sub-expression. Obviously, each sub-expression can be replaced by A or B or C. So you can have things like A minus B minus C minus A minus B. So these are all minus sub-expressions. So this is generating a sequence of A, B, C's with minuses between them. So this can be written in 2 or 3 or many different equivalent ways. So here is another one. He says sub-expression is variable minus sub-expression or variable. And then what is variable? Variable can be A or B or C only. Or I can say sub-expression is sub-expression minus variable or variable. So now he made permutation of this variable and sub-expression, or variable, and variable can be A or B or C. So all these 3 grammars are syntactically equivalent because they are generated A minus B minus C minus B minus A and this kind of expressions. But semantically, they are different. So it is not the same thing. So here is example of G2 parse 3. So G2 says sub-expression is variable minus sub-expression or variable. So you have sub-expression is variable minus sub-expression, and this is also variable minus sub-expression, and you go any way deep that you want, and then the sub-expression is variable, and variable is C. So we have here A minus B minus C. Okay, so what is wrong with this, or what is good with this? Well, it is wrong because the associativity is wrong. what you first do, you compute B minus C, and then you say A minus B minus C. So if you have A minus B minus C, this is executed right to left and not left to right, as it should be. Therefore, the idea is that associativity should be left to right, not right to left. So this G2 grammar is creating results that are different from G3. So it should be sub-expression minus variable and not variable minus sub-expression. If we do that, then you say sub-expression is sub-expression minus variable. This is sub-expression minus variable, and so on and so forth. And then sub-expression can be variable. Variable can be A or B or C. So when you look these three now, you have that you first perform A minus B. When this is done, you say minus C. So A minus B minus C will be executed left to right in proper order. So what Weber wants to show is that regardless of having three syntactically equivalent expressions, BNF expressions, that we are having completely different interpretations in this case, particularly between 2 and 3. So this 3 is creating the correct value, and 2 is creating wrong associativity, going right to left. And this is the reason why we have to be careful when we define syntax, because by defining syntax, we also define semantics to some extent. And this is the message that comes from this lecture today. So let us see more examples of similar things, how syntax and semantics are interrelated and how they affect each other. So we want the structure of the parse tree to correspond to semantics of the string, not just to have syntactically correct strings, which is good for lexical analyzer and syntax analyzer, but semantic analyzer must be also satisfied. So this makes, of course, design of grammar much harder, because you have not only to create syntactical analyzer, but you have also to affect semantics in a way that is appropriate. So that's the reason why we have that this has to be taken into account. So in this chapter, in the textbook, Weber is speaking about operators, precedence, associativity, then about if then else and dangling else, that is also something that is consequence of syntactical definitions. About EBNF, which we are going to skip because we studied EBNF in some detail in previous lectures, and then about abstract syntax trees. So let us see first few things about operators. Operator, of course, is defining what operation will be performed with some arguments. And this can be arithmetic operation or logic operation, or can be operator that is unary or binary or ternary, etc. So here is terminology. Operands are inputs to an operator, like for example, 1 plus 2. Plus is operator, 1 and 2 are operands. Operator can be unary if it takes only one argument. For example, if you say plus plus k, then plus plus is increment operator, and applied to k, it is going to increment k by 1. And of course, minus is also unary operator. Binary operator, like 1 plus 2, has two arguments, 1 and 2. Ternary operators have 3 arguments. So A B, and C. A is a logical value. If A is true, then we execute this part B. Otherwise, we execute this part C. Okay, so this is ternary operator, unary, binary, and ternary. We don't have quaternary operators that would be given as operators, but of course we write functions that have any number of arguments. So if you go above two, most frequently are two operands. If you have more of them, you usually write functions. Now, in most cases, operators are used in infix notation. That's what most natural languages are doing. They use infix notation, and that is what we use in algebra also. However, there are some natural languages that use different way of expressing addition. As far as I know, Turkish is one of them. So you don't say A plus B, but you say A, B plus or plus AB. We are going to add A and B, or A and B should be added. So if you say plus AB, then you have prefix notation. And if you put operator after operands, you have postfix notation. And this postfix notation is, for example, used by old Hewlett-Packard calculator. I don't know, do you have some of these calculators? They used to be very popular 30 years ago. So you have an operand and you push that in the stack. And then take the other operand, B, push that in the stack. And then after that, click on plus. And it is going to add these two operands. Or if you put A to stack and B to stack and then press multiplication, it is going to multiply these two operands. So postfix notation was used also on calculators that use stack architecture. Or A plus B, this is also used on calculators. This is infix notation. So we have infix, prefix, and postfix. And we are going to speak about that when we speak about procedural programming, which is going to start today. We have also unary operators, similarly, that can be prefix or postfix. So if you say A plus plus, then this plus plus is applied to A. And this is postfix operator, increment by 1, or this minus 1, take value and convert it to negative value. Now, first, a few things about precedence. Here is the grammar that was given at the beginning, this grammar G4, that says expression equals expression plus expression, or expression times expression, or expression in parentheses, or A, or B, or C. So when you write grammar in this way, as this G4, what is the intention? Well, you have this little assignment in your homework to write one set of rules that define the expression. Okay, so expression in this little example consists of additions and multiplications. So you can say something plus something, or something times something, or another expression in parentheses. So each expression can be substituted by expression in parentheses. So that's perfectly okay, no problem with that. So you can have here an expression in parentheses multiplied by another expression in parentheses, and that is going to be legal. And then each expression can be substituted by A or B or C. So you can have A times B plus C times A, etc., etc. So this looks that this is like a language of arithmetic expressions that are using parentheses and plus operator and times operator and three variables A, B, and C. So when you take this grammar G4 and you write this kind of expression, you have that expression times expression, and expression is expression plus expression. So that's what we had in this previous example. And then each expression is substituted by a variable. So you have A plus B times C. This is perfectly okay. A plus B times C is the correct expression, except that the semantics of this is wrong because it is going left to right and not taking into account precedence, because the precedence in algebra is that multiplication has higher priority than addition. So if you get A plus B times C in some mathematical textbook, you will say we are going to multiply B, C first, and then we are going to add A. So the precedence of operator multiplication has to be higher than the precedence of the operator addition. And this here is wrong because it says A plus B first multiplied by C. So practically you have here invisible parentheses around A plus B. So first compute A plus B, then multiply A plus B with C, which is not the way how this should be interpreted. So practically, we should first compute C times B and then come and add A. But syntax rule that is implemented here is as a side effect, making the wrong semantic interpretation. So definition of syntax rules is indirectly affecting the semantics of the language. And this makes the life much more difficult when you define language, and you have to be careful that you define both syntax and semantics at the same time. So now we have to fix this, and this precedence can be fixed in the specific way so that most languages put multiplication at a higher precedence level than addition, so that this is interpreted A plus B times C. So that's the interpretation that we would like to have, not opposite. There are precedence examples in many languages, and some languages have plenty of precedence levels. I think that C++ has somewhere around 30 that nobody, of course, can learn. And C has 15 levels of precedence, which is obviously too many. And then Pascal has 5 levels of precedence, which is not enough. So when you write something like this in Pascal, it is going to take 0 or 100. And if this is taken into account, then you have that you get the wrong result. What you have to put here is parentheses around A less than or equal to 0, or parentheses here. And then you first compute this true or false here, and then you compute true or false here on the right-hand side. And then after that, you perform OR operation between these two logic values. So that will be okay. In the case of too many precedence levels, this here is completely legitimate expression. However, when you write this kind of expression, it is very unreadable. And I don't know, have you ever had time to go to internet to see the world championship in writing unreadable C code? There are world champions in that discipline. There is huge competition. And with this here, you couldn't do anything because these are whole programs written in absolutely unreadable way. And then there is the committee that is deciding which one is the best, the most unreadable, and that is the world champion in that discipline. So this one here, you can, of course, interpret when you see this question mark here. So you know that if there is question mark, there should be colon. So here is question mark, here is colon, and you say, aha, now I know that this here is logic condition, and this here is an expression that has here a pointer, and it has plus B times C. So this is arithmetic expression, and this here is some shift And this is not unreadable, but it is obviously not a pleasure to read it. So the good taste is to have around 10 levels of precedence, not more than that. If you have too many of them, that is, of course, something that compiler can use, but humans cannot learn easily 30 precedence levels unless you write this day and night. So you have to see what is the precedence table from time to time, or just put parentheses and don't think about precedence at all. Put parentheses and then you decide precedence, and then you don't have problems at all. So these are examples of precedence. Some languages like APL or Smalltalk have only one level of precedence for all binary operators. So operators are performed right to left. So you have, starting from the right-hand side of an expression, you go towards the left, and on the left you have x equals, for example, and then put everything in that x. So from right to left without parentheses, you can compute an expression. Going back to grammar G4, one that was defined earlier, we have that the expression is expression plus expression, or expression times expression, or expression in parentheses. This created the wrong precedence. In order to have the correct precedence, what you are going to do in your homework is that you separate additions and multiplications. So in the first line, you put all additions. So expression equals expression plus expression, or multiplication expression. So you have addition of two expressions or something that is product. If you do in that way, then the lowest priority operations have to be at the beginning. So additions and subtractions should be here. And then multiplication comes in the next line. So subsequently, you have multiplication expression is multiplication expression times multiplication expression. So you have product of multiplication expression. And then multiplication expression can be replaced by expression in parentheses, or by A or B or C. Of course, in your case, you will have here variables that are much wider spectrum than A, B, C, but this is the general idea, like this G5. So if you go with G5 and make the parse tree for A plus B times C, now you see that you have that expression plus expression, okay? And then this expression is replaced with multiplication expression. They are multiplied, and then you have that they are B or C. So what you have here is that you have left to right associativity, and you have also that precedence, this multiplication is performed before all these additions. Okay, so when you have the tree is also telling you the order of executing these operations. So how is this used by the compiler? Well, you first come and push this C in stack. Then you push this B in stack. Then you perform multiplication. So it is push B plus push C multiply. Then you have this value here that comes as the result in this place. Then you have to push A in the stack. And then you have A and product in the stack. And then you come and make addition. And so you have that the compiler has to produce the following: push C, push B, multiply, push A, add. So this is what compiler is doing. And then if you have stack architecture, if you have another kind of architecture, then you have, for example, multiply BC and put result in an accumulator, or put result in the register, and then multiply, then add this register with register that contains A. And then you will have different assembly language, but This depends, of course, of the processor architecture that you have. But the precedence will be correct. We first multiply and then we add. So it is the same language as before, but it has parse tree that has correct precedence. Now, few words about associativity. Associativity, of course, is a similar problem, because if you have these two parse trees, they create A plus B plus C. So you see plus here and plus here. So it is A plus B plus C, and here also A plus B plus C. So this grammar G5 that was very nice here to generate correct precedence is having ambiguity in defining the associativity rules. Because if you have this interpretation here, therefore, if you have that the expression is sum of two expressions, an expression can be replaced by multiplication expression, as we have here, and then multiplication expression as A, B, or C, then you can have you can have situation where we have that the associativity is right to left. So you first perform B plus C, and then we add A to that result. So this is going right to left. And of course, that is not the way how arithmetic expressions should be executed. They should be executed and interpreted left to right. So we first add A plus B, and then add C to that. And this is the way how this should be done. So obviously, this grammar G5 has problem that is not creating unique and correct associativity, which should be left to right. First A plus B, and then C. So A plus B plus C should be left to right associative and not right to left, not in opposite direction. So how to fix that? Well, you can fix that in a variety of ways, but before we do that, it is interesting to see that some operators are left associative, like A plus B plus C plus D. It is assumed to first perform A plus B, and after that, the result with C, and after that, the result with D. So there is also one pair of parentheses that was not written here, but you have that even this returns a value, and this value can be used then in some way. Right associative operators are going right to left. So first perform C plus D, then B plus this intermediate result, and then A plus the other intermediate result. And you get A plus B plus C plus D in this way. So most operators in most languages are left associative, but there are exceptions. For example, exception that everybody knows is assignment in C, C++, and Java. So if you have assignment A equals B equals 0, how this works? That's the question. Okay. Can somebody tell me how this works? Just unmute your microphone and tell what you say, what you think. Okay, it is written here. It is left, it is right associative as assignment. So in C, C++, Java, similar languages, you have that first we perform B equals 0. Now, you have here parentheses, invisible parentheses between this equality sign and B, left parentheses and right parentheses. So when you perform operation B equals 0, 0 is going to be stored in B. But after that, this expression B equals 0 is going to return the value. And this is something that is very important, because there are languages where you have that the assignment has the quality of expression. Expression is always defining returning a value. So if you say a equals 3 plus 4, that means you are going to take 3 plus 4, and this is going to be 7, and this returns a value. However, here b equals 0 also returns the value, and this value is 0. So then you have that the next step is a equals 0, because this is what is returned from this operation b equals 0. Now you have a equals 0, and of course this 0 is going to be stored in a, but a equals 0 is again going to return 0. So this a equals b equals 0 is returning a value 0. And you can ask, who uses that 0 and why we need it? Of course, nobody uses that, and that's perfectly legitimate. But if you have this kind of expression that is legitimate in your language, like in C++, then you can write only the number 0 and put semicolon after that. And this is not going to be an error, because 0 is an expression. Expression that nobody uses is correct expression, and therefore it is acceptable in C++. So put 0, you put semicolon after that, compiler will say, aha, you have here a constant, nobody uses that constant, then I can kick that out and will continue without problem. So this is consequence of multiple assignment, A equals B equals C equals D equals whatever. Okay, so that is right to left associativity in this case. For example, Fortran up to 77 was not right associative in assignment, simply because assignment was strictly operation that is non-functional. It is not returning a value. So when you say b equals 0, you take 0, store it in b, and return nothing. You cannot perform any operation with that. In this case, a equals b equals 0. You can put this in parentheses and multiply it by 3.14, and it will be perfectly okay. Okay. So in most cases, associativity is left to right. So a divided by b multiplied by c. That would be left to right associative. And here in Fortran power function exponentiation, a to exponent b to exponent c, you first compute b to exponent c, and then a to exponent that is obtained here. Because this could go also left to right or right to left, but it is going right to left. That's how it is defined, same as this one here. Associativity in the grammar that was wrong in this way can be fixed by writing a seemingly equivalent grammar, G6, which is now written as expression is expression plus multiplication expression or multiplication expression, same as the first line here. That is okay. However, when we go to multiplication expression, we say multiplication expression is multiplication times root expression, or root expression, where root expression is expression in parentheses, or A, or B, or C. So now we had to introduce the third line that is having this expression in parentheses. And by doing that, we are getting now that addition is working properly, because you have here expression plus multiplication expression, and then root expression is a, root expression here, root expression here. So you have that it is going left to right, a plus b plus c. So it is generating the same language as before, but it has now correct associativity, not incorrect associativity. So associativity in expression should be consistent with rules of algebra, and therefore you cannot do it in an arbitrary way. So here is another exercise of expanding this grammar. We are not going to do that here, but we'll spend a little bit of time speaking about other ambiguities, in particular ambiguity of so-called dangling else. Dangling else is the situation where you have that syntax definition is not giving you explanation of correct semantics. So associativity has to be somehow solved so that it is not creating ambiguity. And ambiguity is exemplified here. So if statement has if expression 1, then if expression 2, then perform S1, else S2. And the question is that I have here two if, then, and here is else. Okay. So my question to you is, whose else is this? Does this else belong to this if here, or belongs to this if here? So can somebody tell me what is the rule as given in 210 class? What is the rule for this ambiguity here? Because you can write it in this way in C++ or any similar language. Is there anybody who knows whose else is this? First if or second if? This seems as a mystery. Okay. And the rule that is given in 210 class is that else belongs to the closest if. That's what I tell you in week 2 or week 3 of the class, that if you have if then else can have, or then part can have nested ifs. So if inside if is perfectly legitimate, and else always belongs to the closest if. Therefore, what we have here is if then else, where this else belongs to this if. So it is as this is in parentheses. And then you have a skip statement. If condition, then either perform this if then else or don't perform this if then else. Okay, so that is example. And now how to write the grammar, the syntax. So it says statement can be if statement or statement 1 or statement 2. Okay, so now let us say what is if statement. Okay, if statement is written as if expression, then statement, else statement. And each of these statements can be if statement, okay, or can be if then statement, if expression, then statement. So this else is omitted. And then you have the possibility to say what is expression. Expression is E1 or E2. So this grammar written in this way is creating this expression here, which is legitimate expression, but it does not tell you whose else is this, because you can write that in two different ways. You can say if expression, then statement, else statement, and then put inside if statement, then this statement. And this is obviously wrong interpretation, because in this line before will be if E2, then S1, else S2. So this here, that according to additional explanation belongs to the closest if, is not defined in that way. It is defined as belonging, this else belongs to this if, then else. So this else is related to this if. And when we write it in this way, syntax, it is going to be interpreted that belongs to this if. So it is not clear what happens. The other situation is to say if expression, then statement, and then this statement is if then else. And this is the correct interpretation. But both of them are generated by this grammar. Therefore, this is the way how the grammar should not be written, because it creates semantic ambiguity, and this is not acceptable. Therefore, there is way to eliminate this ambiguity so that you have the problem with this statement. So we can define one full statement, full if, and then work with that. So this is not important how to eliminate that, but it is important that we have possibility to eliminate this ambiguity. And therefore, the bottom line of this presentation is that there are cases where we have to think about semantics, and correct parse tree is obviously this one. So the syntax has to be written in a way that gives you this parse tree. So if expression then, and then you have here another if statement. So if expression then, if statement, if then else. And this is perfectly okay.
What types of languages would have an ambiguous expression evaluator?
No language has ambiguity in that, because you have always rules that clarify that. So there is no language that has ambiguous things, because that is designer of language has to eliminate that. So that's a good question, but you don't have ambiguities. But the question is how to eliminate them. One elimination is one that I mentioned before. So when you come here, when you come to 210 class, whoever teaches if statement, the first thing that has to be, how do you teach if statement? You say if statement has condition, and then if condition is satisfied, you perform the first part, otherwise the second part else. So if condition here, if this if is satisfied, you perform E2, you perform S1, otherwise you perform S2. And then the next sentence is, you know, S1 can be another if statement, and S2 can be another if statement. So if you have plenty of these ifs, thens, and else's together, how to solve this problem? They are not going in 210 or in any class write syntax definitions for you. They're just going to explain in words how to implement the semantic rule. And will tell you else belongs to the closest if. Do you understand that? Everybody will say yes. Okay. And now the problem is solved once forever. So you have this that can be interpreted in an ambiguous way. However, the compiler is written in a way that interprets this perfectly okay, that else always belongs to the closest if. So when you have this else, compiler is finding where's if and putting this if then else in parentheses, and then computing whatever comes from here. And then if E1 is satisfied, then it is going to go to this if statement. Otherwise, it is not going to go. And this is what is done in words. Therefore, by saying, you know, else belongs to the closest if. And that's how this is done. And if they didn't tell you that in 210, then you go back and say, give me my money back. I paid you to teach me that. So this has to be said the very first moment when you speak about if statement. So going back here, this is the correct parse tree. Okay, so here is a practice, an example that is given by Weber, and he asks you to tell what is the value of A at the end of this statement. So can you quickly think, and can somebody tell me what is going to be A?
Can you repeat the question really quick?
Huh? The question is written here. What is the value of A after this fragment executes?
Oh.
A can be 0, or can be 1, or can be 2. So which one?
It would be 2. The answer would be 2. 2.
Bravo, 2. Bravo, 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 bravo. Yes, can be 2. Can be 2. Now, why you have to spend some time thinking about that? Why you didn't reply immediately? It is 2.
Oh, there was a small delay for me because I got like a few seconds delay. So I just like, I didn't hear you. It was lagging a little bit too. So yes, that's what happened with me.
Yeah, okay. But there is another thing that you can notice here. This is intentional wrong indentation, because Weber indented with if and else to mislead you that this else belongs to this if, because he put them one above the other. That's what he wanted to do, okay? So you have that if 0 is 0, this is true. Therefore, you are performing this if statement. But it looks as if this is true, then that this else belongs to this if. So programmers have to properly indent the code, because if it is not properly indented, then you cannot have the proper interpretation quickly. You have to think about that. So let us discuss that for a second. So here is what Weber is saying about that. And I'll tell you immediately that I fully disagree with what he is saying. But what he is claiming is this. First, you have to put correct indentation. Like, okay, we agree with that. So what he said, put integer a is 0. If 0 is 0, then if 0 is 1, put 1, otherwise put 2. So since 0 is not equal to 1, you will have a is 2, and 2 is the result. But then he comes and say, even better, use of block reinforces the structure. So he is putting this pair of braces around a single statement, which I would say, do never something like that. Don't put braces around a single statement. And my disagreement with this, which you can accept or not accept any way you want, is this one. The way how I write my code is, if statement is very simple, like this one, I always put it in the single line. So say if 0 equals 1, return a is 1, otherwise a is 2. This is so short, so readable, so trivial that you don't have to put that in 3 or 4 lines. You just write it in a single line. Make it short, simple, readable. Okay. And then, of course, indent it. So if 0 is 0, this is true. Therefore, we are going to execute this line of code. That's how I write my programs. I suggest you do the same. Or if you don't like it, do something else. So another thing that I suggest, never put braces around a single statement. It is redundant, and blocks should contain 2 or more statements. And never put braces that are not one above the other. Because if you have here not one statement, but 100 statements, then you have this brace here somewhere on the next page of your code. And you want to see where is the beginning of this. Well, the beginning of this is hidden somewhere on the right-hand side. How are you going to find the beginning? You have to count, to go crawl to this code to find where is the beginning that somebody wrote, who knows where and who knows when. Put braces one on top of each, one on top of the other, so that you see where is the beginning, where is the end. That's my suggestion number 2. And then we can speak a little bit about languages that don't dangle. And Weber says there are languages like Ada that have if statement that is terminated with an end if. And this is the way how you can solve that problem.
Hey,
Not
Bash has that too.
Huh?
Bash has that as well.
All good languages have that. And whoever has different is a bad language. So let me tell you about style of if statement. So here is a piece of C++ or C, which is an exhibition of bad decisions. Look what happens here. You say if 0 equals 1, you have to put that in a pair of parentheses. Then you have here A is 1, B is 2, and this is pair of braces. So this is the then part. Then you have else, and then you have pair of braces here. A is 2, B is 3, and this is the way how you must write this in C++. Okay. Now, this is an exhibition of ultimate bad taste. It is wrong, wrong, wrong for many reasons. So how to criticize this here? Well, the first thing, what the founding fathers decided, not to have and if here. So if we want to say how this should be written in any of readable modern language, it should be if, then, else, and if. So if is the beginning of an expression, and if is the end of an expression. And if this is a functional languages, this is left parenthesis, this is right parenthesis, and that returns a value. Okay, sometimes. Even if it's not returning the value, then you write like this: if 0 equals 1, then you have the sequence that is performed if then is satisfied. Else, you have another sequence that is performed, and after that you have end of if statement. Now, this is readable, and it is not using redundant delimiters. Because pay attention, what is this? This here is the condition. How to find the condition? Condition is whatever is written between if and then. Therefore, the compiler is finding the keyword if, and then knows that after that comes then. And between if and then, there is condition. So condition is extracted without any problem. Look at here. You have that this is for delimiter, but you have another useless delimiter. This is this left parenthesis. And then here, right parenthesis is delimiter between this condition and this expression here. But you have another brace that is completely useless here, should not be here. Okay. And then you have here else, and again, pair of braces. So how they made this terrible decision to write in this way? The sequence of errors is this one, bad decisions. First, there is no and if. And since there is not and if, you don't know where is the end of the statement. So this decision not to use and if forced them to put here left brace and right brace. Once they decided to put left brace and right brace, they said, well, we will put that also here because of consistency. If you have sequence with 2 braces here, we will need sequence with 2 braces here as well, regardless that I have here else. Then the other terrible decision was not to use the keyword then. So it was necessary to use else. So what is difficult not to use then? If something, then something else, something, that's English. Why not to use then? But I decided not to use then. So what happened after that? If you don't have then here, then you have somehow to separate this 0 equals 1 and this else. And instead you can have only one statement, A is 1. So this decision not to use then had the consequence that you must put parentheses. So here is if, necessary, unnecessary parentheses, 0 equals 1. And then you have here no then, and then you have to have these 2 braces and else. And some people even write in this way, which is criminal. It is, well, it is unreadable. It is absolutely a show of bad taste. But we do that for salary. And I write C++ code with pleasure and get paid for that. But I don't think that this is good. This is how the things should be. This is good. Okay, good taste. This is bad taste. So I know, of course, that half of you disagree with me. Enjoy. If you want, put your semicolons and braces from now to eternity. But if you don't have to do that, don't design languages in this way. This is absolutely unacceptable. Another thing, all of them have terminators. Look at this, semicolon, semicolon, semicolon. Who needs all these terminators? What is the reason for that? Because this language does not want to recognize that you have end of line at the end of each line. So this line here has end of line at the end, which is not visible, but it is there. So why this cannot be delimiter between first statement and second statement? Why you have to put these semicolons, idiotic, at the end? Here, you have semicolon, but only if you separate A is 1 and B is 2. So this is the separator. This is not the terminator. Because after this B is 2 comes the keyword else. And this is separation between this expression and else, because this is word delimiter. Word delimiter is if, then, else, and if. Therefore, or some languages put just and here. So if, then, else, and if are word delimiters, and these are expressions or whatever you have inside. And this is good taste. This here is bad taste. It is inconsistent. It does not have the end. It is the beginning without end. Okay. So now you say what you think about that. You are going to say, we disagree. That's our native language, and everybody likes the native language, whatever is your native language. Huh? Is that so?
Personally, I prefer Python.
Yes, I prefer Ruby. you have this one that is written this way in Ruby. Ruby is an exhibition of good taste, unbelievably good taste in everything in defining syntax and semantics. So, except of love for Python, do you have? In last section, I asked the same question that I said, but I still love this one here. I said, why you love it? Because it is my native language. Of course, everybody likes your native language. But the point here is that all languages deserve respect, even those who have bad taste for syntax. Because anyhow, when you write something like this, you are never thinking about syntax. You are thinking about meaning and functionality that you want to have here. So you want A and B 1, 2, or 2, 3. And this is what is in human mind. Nobody has in mind these braces and semicolons. This comes automatically. This is something that you learn after first week of programming, and after this you don't need anything more. So this is perfectly okay. But on the other hand, you have that if you have to write all this decor around these two little statements, then it is more likely that you are going to forget one of these braces, or if you have to read that, it is going to be obviously less readable than something else. You know, so it is better to have more readability. Now, Weber is speaking also about cluttered grammars. We are going to skip that. And about EBNF. He said, okay, in EBNF, you eliminate recursion by having X inside pair of braces, which means 0 or more repetitions of X. And then you write that in this way. And so there is also a story about abstract syntax tree. So this syntax tree can be replaced by this simplified notation. When you say A plus B is written AB plus, and then the result plus C is written in this way. And this is practically the end of syntax, where the conclusion is that grammar defines syntax and more, so that grammars or syntax rules contribute also to the definition of semantics. And we have to be, if we write compilers, then we have to be very careful about that to have it done in a proper way. So this is the way how we can complete our story of syntax. And I don't have anything more to tell you about syntax. Now is the time to go to procedural programming, which is part 2 of this class. Do you have, please, any question regarding to this segment of syntax? Something that you want to ask before we continue? Do you see this slide, procedural programming?
Yes.
Yes, it is shared. Okay, thank you. So we finish syntax. You are going to make your homework, and after that we will have midterm with that. So now is the time to study a little bit syntax and do the homework. Let us say a few words about procedural programming. The good news is we are on time. The bad news is that there are 360 slides here in the corner. So this is slide number 1. What we are going to study are basic data types and formats, numeric accuracy, procedural programming paradigms, language-independent programming, comparison of languages, structure theorem, operators, expressions, comparison of algorithms, brute force programming, and problem solving, program performance control and improvement, data types and conversions, and performance of array processing. All these are important components of procedural programming. Procedural programming has simple goals: make program short and make it fast. So how to make short and fast and efficient programs? Of course, this also includes working with numbers, and working with numbers has basic data types, data formats, and numeric accuracy. So definition of precision, range, overflow problems. Of course, this is something that is topic in 210. I am teaching that in 600 because people who teach 210 don't do that. This is the reason why this is here, not that this belongs to 600. So let's go quickly through that. Integer has overflow and underflow, and real has also underflow and overflow. And precision, significant decimal digits are limited, and addition A plus B plus D is not commutative. It is not A plus B plus C equal to C plus B plus A. So you have all that on computers that we use, and you have to be aware of that. So let me quickly remind you what are the binary codes for basic unsigned integers and integer. In the case of unsigned integer, 0 is coded with 3 bits, if you want, as 0, 0, 0. Then the next is 0, 0, 1, 2, 3, 4, 5, 6, and 7 is 1, 1, 1. So this left is binary, this here is decimal. But if you want to have a number that is positive or negative, signed integer, then 0 is going to be 0. You are going to have 1, 2, and 3. And this is going to be the end of the world, because you cannot go with 3 bits further than 3. If you add 1 to this, you get 1, 0, 0, and this is minus 4. So minus 1 is always coded as the sequence of ones. Minus 2 is 1, 1, 0. 1, 0, 1 is minus 3. This is minus 4. So you see what happens if you take binary 7, 7, binary 1, 1, 1, which is 7. Add 1 to this, you are going to get 1 with 3 zeros, which is this 0. So you have practically a ring of unsigned integer where after the largest value comes 0. Here, after the largest positive value, if you add 1 to this, you get 1, 0, 0, which is minus 4. So after plus 3, you get minus 4. You again have a ring. Therefore, unsigned integers are written in a ring that has the smallest value 0 and the largest 2 to n minus 1. So you go 0, 1, 2, 3, up to 2 to n minus 1. And if you add 1 to this, you get 0. If you subtract 1 from 0, you get 2 to n minus 1. And of course, these errors are perfectly visible and frequently encountered in programs. So we have to be perfectly aware of this problem and never permit this to happen. Same thing is with integers. If you have positive or negative integers, the largest positive integer is 2 to n minus 1 minus 1. And the absolute value of the largest negative integer is 2 to n minus 1. So you have the ring of numbers where you have that numbers are going from 0, 1, 2, 3, up to 2 to n minus 1 minus 1. If you add 1 to that, you get minus 2 to n minus 1. So you jump from positive numbers to negative numbers. And this can create terrible errors in your program. So you have to be very aware that this is never happening in your code. So that is why we are studying this here. So you can say that if you add 1, this is movement on this ring for one position in clockwise direction. If we subtract 1, we go in counterclockwise direction. If we are here in the range inside this ring, inside this border between positive and negative numbers, everything is perfectly okay. We go left, right, no problem. But if we jump from largest positive number, we are going to go to largest negative. If we subtract from largest negative, we jump into positive numbers and get completely wrong results. So this is something that has to be taken into account very seriously, that happens in programs that you write. Same is with unsigned integer. If you have big value, and for example, if you have 6 and add 4 to 6, what is the result? Well, 6 plus 1 plus 2 plus 3 plus 4. So 6 plus 4 is 2. That is what you are going to get. And if you say 2 minus 4, 2 minus 1 minus 2 minus 3 minus 4 is 6. So 2 minus 4 is plus 6, which is completely wrong. And this is happening in each and every computer, including your laptops and desktops. So how to see this problem? Of course, the cheapest way to see that is to write programs with 8-bit integers, because 8-bit integers are going in what range? If you have character variables, so I have character A, B, C, D, or C and D here. So if I have character variables, they have how many bits? 8. 8 bits has each character. And if we have 8 bits, that means that the largest value with 8 bits is going to be, if you have signed integers, it is going to be 2 to 7 minus 1. Okay, and 2 to 7 is 128, minus 1 is 126. So what can fit in the single byte is from minus 128 to plus 120, 120, not 6, but 7, sorry. So 127 is largest value, minus 128 is the smallest value, and nothing more. Now, you would say, why should I use single byte? But because it is having enough memory for small numbers, and it can be very useful for solving graph problems. If you want to have something that is very fast, you can have that graphs usually don't have millions of nodes. There are plenty of problems that have, let us say, 200 nodes. If you have 200 nodes, then you can put each node in a single byte, because in bytes you go from 0 to 255 if this is unsigned integer, or you go from minus 128 to 127 if this is the signed integer. So in my little program here, I have signed integers, and I have two values, 130. So I want to add 100 plus 30, and I want to subtract minus 100 and minus 30. When I add 100 plus 30, then I am going to write here this 100 plus 30 equals the result of this addition. So it is add C plus D. So that's what I put here. And I have to write that as an integer. So I said integer of this value. So what is the result printed? It is 100 plus 30 equals minus 126. Okay, so it is completely wrong. giving me that the sum of two positive numbers is a negative number. Well, that's criminal. How this happens? Well, I have to get 130. And the circle of integers is 126, 127, minus 128, 27, 26. So what I'm having here, I want to have 130. So here is 127, 8, 9, 30. So what has to come as the result is minus 126. Of course, it is wrong. It is wrong, and here it is. No doubt about that. Then I have minus 100 minus 30. So how this works? The largest minimum integer is minus 128. After that, we jump to 127. So if I have to get minus 130, I have 128, 129, 30. So I get plus 126, which is displayed here. So it is wrong completely. If you work with unsigned integers, so you say unsigned character, add, subtract 127 and 30. So if I want to add or subtract these things, I get that 127 plus 130 equals not what I want to get, 257, but I am going to get 1. And here I have 127 minus 130 is plus 253. So you can see from these rings here how this happens. So if you want to see this phenomena, always work with character variables because this is easily visible. But don't think that if you have integers that it is going to be different. No, it is going to be the same kind of problem. So here is short integer. If I say unsigned short and have short integer, then the largest value in short integer is 2 to 16 minus 1, which is 65,536. So if I go and take 65,531 plus 1, 2, 3, all these are correct values. If I add 5, I get 0, because this is 65,535. This is the largest unsigned integer in short format. You add 1 to this, you get 0 immediately. So that's tragical. The same is if you subtract. You subtract 4 minus 3, you get 1. Subtract 4 minus 4, you get 0. Now subtract 4 minus 5. What are you going to get? 65,535, which is going to explode somewhere if you have this as a part of your program. So the same happens when you have short integers, where the largest value is 32,767. And then after that, you jump to minus 32,768. So this here is perfectly correct program, and this here are perfectly wrong results, okay? And this happens always to everybody on all computers, and you have to be aware of that. This is 210 story. I'm not going to waste my time on this. Here is with integers, the same situation, but now the largest value is 2 billion. Other than that, everything is the same. Add to this value 4, you get 7. Add 5, you are going to get negative number, and it is going to be 3 plus 6 should be 9 and not 7 here. It is negative number, and here is the same situation. So when we have these problems, we have we have to be aware of these numerical problems. To avoid these problems, if you have, for example, to compute binomial coefficients, you should never multiply numerator, multiply denominator, and divide these two things. You should always go zigzag. 10 divided by 2, multiplied by 9, divided by 3, multiplied by 8, divided by 4. Because then 10 and 2 will cancel, 9 and 3 will cancel, 8 and 4 will cancel. So you see these diagonals. 10, 2, 9, 3, 8, 4, etc. And here is going to be 6 and 3, so that you always have small values. Otherwise, you have to compute n factorial. you are never going to compute 200 factorial because it is going to explode along the way. So next time we are going to start somewhere from here. So please read this initial part of the this story about data formats and data types, and we are going to continue from here next time. Is there any question that I could answer now?
Couldn't you prevent this simply by allocating an array of ints and then just splicing the big number?
Well, if you have an array of int, you have that each component of array has the same limitations, because each int in the array has to fit in 32 bits if you have standard byte organization where 4 bytes are one integer value.
Right,
Okay.
but if you were to use the array to prevent a single value from overflowing, like you would just split it into half and then you'd have twice as much space to handle the big number.
You can write algorithmic solutions. That's a good idea, but you have to have significant addition of code for that. And another thing is that you have languages like, for example, Scheme that we are going to use, all Racket, that don't have limit on integers. Integer can have infinite number of digits, so you don't have to think about that. In Ruby, you have that integers don't have limit. You have so-called big num that is not visible, big numbers that are integers written as strings of digits, and you can have any number of them. In Scheme or Lisp or such languages, or integers are not limited. But of course, then it is slower. And here is an example that might help to answer your question. If you have to add, how to prevent overflow? If you say, I have A plus B, this has to be less than the maximum value. So that is what you were suggesting, actually, that you say, if B is less than or equal than max minus A, then I can perform this addition. Otherwise, I cannot perform. I have to do something different. Okay. And if you have an array of int, you can have an array of digits. Then you can say, I can have an array where in each integer or in each character, you put a single digit. That's how COBOL works from day one. They had always the digits are stored, each digit in 8-bit byte. That was the way how they work. The same situation happens with multiplication. If you have to multiply two values, what's going to happen? You can have an overflow. So if you have an overflow, what's going to happen? A times B divided by B is not going to be equal to A. So before you decide to overflow, you check, to multiply, sorry, you can check whether A is equal A times B divided by B. And if it is, you can multiply, everything will be correct. But if this is not the case, if A is different than A times B divided by B, never multiply A times B. So you can put these things in a critical part of code, but you have to write more code, and it's becoming more less readable and slower, which is also not good. But you cannot have free lunch, okay? You have to pay somehow for that. So is this somehow something that you expected to hear or something else?
No, that pretty much answers it. Thank you.
Okay, thank you. Any other question?
No, like, thank you. And also, like, is the apocalypse, Professor? Is the apocalypse?
Yeah, if we, there is the only one thing that is missing. That's the question for everybody. What is missing now? An earthquake. We have everything.
I know, no, yeah, yes. We have the air. Like, oh wait, also
you better knock
tsunami.
on some damn wood.
Also, a tsunami might make it better too. A tsunami.
Yes, it is complete apocalypse. It is completely dark as in the middle of the night. Exactly. So
Yeah,
everybody.
I know,
Yeah, so don't worry. This is actually one of those late night classes taken after
Oh yeah,
8
it's
p.m.
late night. Yes, it's a late
like
class.
that.
It's
So
actually
don't
12
worry.
a.m.
Anyhow, if you have some questions or something like that, or interest in homework, so there is also office hours today after midnight.